Guys, a short video here on introduction to Manova. This is just going to put the Manova technique in, no, I don't know, I guess in proper perspective with the ANOVA family. So going to use some examples here, and we'll get into the theory at the right time. But Manova is just multivariate analysis of variance, or multiple analysis of variance, and it's a very powerful technique. If we have more than one dependent variable, in other words, if we have multiple things that we have measured our subjects on, and we find that those things are highly correlated, then it's appropriate to conduct a Manova. And just to put this in proper perspective, what I want to do is kind of run through some examples with you. So, you know, kick your shoes off, prop your feet up, and hopefully enjoy. I don't know. Guys, ANOVA, you know, presented in the simplest form, analysis of variance, and it just examines the difference in group means, where we have more than two levels. And obviously, if we have two levels, we run a independent samples t-test. But if we get three levels to control for the family-wise type 1 error rate, we conduct an ANOVA. So the question I want you to kind of think about, and I'm going to build on this, we currently have three people at Shawnee who are teaching statistics regularly, Dr. Dev Koda, Heather Wall, and me. And let's say that, you know, we're sitting around, we're wondering what kind of, you know, what's the best way to teach Math 1500, and believe it or not, we do have those kinds of discussions. And Dr. Dev Koda says, well, I think my Stat Lab is the best online course management system. And Heather says, well, I think Stats Portal is the best. And I'm like, yeah, I really don't care. I just think it's important that we use R. Now, I don't even really, this is clearly fictional, because I don't even think that's the way that we would feel. But, you know, again, just an example. Okay? So, guys, there are two estimates of the common population variance, the between variance and the within variance. And clearly, ANOVA gets a measurement on the ratio of these two variances by looking at the F statistic. Guys, remember again, between variance is the variance of the means around the grand mean, and the within variance is the weighted average of the variances. And if you look at the formula for the F statistic, that's pretty clear. Now, more review of ANOVA. If we you know, we call ANOVA omnibus, and it's because it's this grand procedure that tells us if differences actually lie, if there are statistically significant differences, but we need other things to examine those differences. We just went through a sequence of videos on planned comparisons. And remember, contrasts are planned before the data is collected. The reason being is it's kind of standard procedure in an orthogonal contrast that we compare levels or chunks of variance of our experimental and control groups. And obviously, if you have some well laid out plan there, you want to collect your data to where you can appropriately carry out your contrast. Another approach is just kind of the all-in approach, which is called post hoc, and those are only conducted if your ANOVA is statistically significant. So, guys, if group variances are significant, then you know, that says we don't have equal variances, and we run an alternative post hoc like Tamhani. And if group variances are not statistically significant, we can run a Tukey, Chaffee, Bonferroni, and so on and so forth. And guys, we can always check equal variance assumption with the Levine's test of equal variances, or the ratio test. So let's move forward into a two-way ANOVA. Two-way ANOVA is applied to a situation where you have two categorical variables and one quantitative variable. So remember, the two categorical variables are referred to as our independent variable, and the quantitative variable is our dependent variable. So we're taking a quantitative measurement and we're looking at the differences across two layers, the first categorical variable and the second. Well, guys, in a two-way ANOVA, these things get a little confusing because you have three F ratios that you look at. One examines the effect of the first independent variable, second, the second independent variable, and the third, of course, looks at the interaction of the two. An example, keeping consistent with the Math 1500 situation. If we have a dependent variable where the Math 1500 final exams are being measured and examined, factor 1 could be the teaching method, and factor 2 could be whether it's an evening or day class. Not only does Twoway ANOVA allow us to look at factor 1, whether there's a statistically significant advantage to teaching with MyStatLab, StatsPortal, or R, it also gets into looking at the differences between evening and day classes, and maybe R turns out to be more effective with day classes while MyStatLab turns out to be more effective with evening classes. So it allows you to come in and examine the interaction between the two. ANOVA, analysis of covariance. The goal is to examine how much of the error variance can be reduced by accounting for kind of leveling out information, if you will. So in ANOVA design, we have, again, one dependent variable, two independent variables, one or more categorical, and one or more quantitative covariate. Covariates can be categorical, but I think that in this class I've treated these as quantitative covariates. So guys, assumptions for ANOVA, again, just as a review. Each covariate should be independent with each treatment. So each treatment is our categorical independent variable. So if we have a covariate such as ACT score maybe, then we would want ACT scores to be equal over each treatment level. MyStatLab, R, and StatsPortal. Excuse me. So we run separate ANOVAs to check, and we want a non-statistically significant result to pull this off. There's another, homogeneity of regression slopes. We want slopes between the covariate and the dependent variable to be similar across groups. There's two ways to check this. You can run ANOVA with interaction variable included. We want the interaction variable to not be statistically significant. Or, well, I really don't go in necessarily wanting statistical significance or not, because it's going to be whatever it is. But the results are, if we have a not statistically significant result, then the assumption of homogeneity of regression slopes has not been violated, and it has been violated if the interaction is statistically significant. So, an example of ANOVA, we could say Y is the final exam score. X1 is the teaching method, and we come in with a quantitative covariate of ACT math subscore. Because at the end of the day, we want to be able to actually tap into the teaching technique. And if there's some lurking variable out there, for example, maybe Dr. Dev Koda, just by way of random scheduling phenomena, got just a group of students who struggle with math more than maybe Heather and or me. Well, you want to control for that. You want to control for the variation in the differences in final exam score that could be contributed to just difference in talent level. I mean, those of us that have been teaching very long at all, we always remember classes of both types. I've had classes at Shawnee and high school in various places that were really, really easy to teach. I've also had some classes that were extremely challenging. Again, that is a pretty simple example of ANOVA. Now, that moves us into Manova. I think that builds kind of a solid foundation on the ANOVA family on things that we've looked at so far. So let's move it into to Manova. So Manova is a multivariate analysis of variance, just as we said, and it's a way to test hypothesis that one or more independent variable or factors have an effect on two or more dependent variables. So what you got to think of now is you got to think about, instead of having like y equals, we have y1 equals, y2 equals, y3 equals. We have multiple dependent variables, not the independent layers, but the dependent variables. So the way I've looked at this is, imagine taking a Math 1500 final exam and partitioning it, that's hard to say, partitioning it into three subsections: descriptive statistics, probability, and inference. Now, if we wanted to examine the differences, for example, in just descriptive statistics across the three teaching levels of Dr. Devkota, Heather, and myself, then we could just run a straightforward ANOVA. But what if we also wanted to examine the differences across probability questions and across inference questions? Well, we would get into a situation where we would conduct multiple ANOVAs, and we get in a situation, a statistical dilemma here. If those dependent variables, descriptive statistics, probability, and inference, are highly correlated, then we run into some issues doing that. And I don't think it's beyond stretch of imagination that students who score high in descriptive statistics may also score high in probability and inference. So stepping back and considering that those three measurements may be highly correlated is not beyond the stretch of the imagination. So guys, thinking ahead a little bit, we can run a Manova design, but we could also control for a covariate or adjust the variation for a covariate, and when we do that, we would call that a Manova design. And I hope I get the chance this semester, I hope we have time for me to put up a couple of videos on Manova. So guys, Manova designs are more complicated. They just are. And a Manova design is also pretty challenging. So we're gonna take it in baby steps. All right. So why should you do a Manova? Well, there's going to be one on your homework assignment. That's one reason you should do it. But you know, when you're out there, and if you do get into research one day, if you do complete the program and complete the master's thesis, when would you consider a Manova instead of multiple ANOVAs? So first of all, again, a reduction of the family-wise type 1 error rate, just like ANOVA does with multiple t-tests. Manova does with ANOVAs. None of the individual ANOVAs may produce a statistically significant main effect on the DV, but in combination they may. And Manova accounts for the high correlations between the dependent variables. Now, if you're taking measurements on things that you don't think will be highly correlated, then go ahead and run multiple ANOVAs. But many times in education research, we take the measurements that are related on the same subjects, and we just need to control for that. All right. Assumptions in Manova. First of all, we have multivariate normality. So the dependent variables must be distributed normally, and the subsets of the variables must have multivariate normal distribution. So what we'll do there, let's just say, for instance, we do have three measures: inference, probability, and descriptive statistics. Then we would look at those, construct histograms of each, and probably run a Shapiro test of normality to get an indication of the normality measure or the normality assumption. The second thing, a homogeneity of the covariance matrices. For ANOVA, the variances of the dependent variable must be equal across levels of the independent variable. for Manova, the univariate requirement of equal variances has to hold for each one of the dependent variables. So to keep from running multiple Levines, there's something called Box's M-test that we'll talk about. And guys, always we need independence, so scores on the dependent measures should not be influenced by or related to the scores of other subjects in the condition or the level. So again, independence is always a biggie in test of inference, unless we control for that, you know, for matched pairs or dependent samples t-test, things of that nature. Okay? Well, next thing we'll do is we'll get into a short video on running a Manova example and jump into R and see how that's done. So show you an example of some data that I have. Now what we've got here is we've got three groups. You might think of it as three treatments, three instructional techniques, you know, whatever. And we have two dependent variables, y1 and y2. So what I have done with this data is I put it into Excel, and you can see that when we put things into Excel, that on the lines we have to have cases, and on the verticals we have to have variables. To save time, I've already gone ahead and you know, set my working directory and imported the data into R. Alright, so I've attached it, and there's our data. So a very small, manageable data set there to deal with. Now, the first thing we'd want to do when we run ANOVA is we have to kind of bind the y1 and y2. And what we do with that is we use the function cbind. And we combine however many dependent variables that we have. Now, the Manova design is kind of wacky in a sense, because what actually happens is throughout the process it kind of takes the two models and it kind of smashes them together and creates what I would call a combined model, maybe a composite model. And it will compare each of the models to that composite. And if there's this drastic difference between the model and this composite, then we'll get statistical significance. So it's not really comparing the two models or three models against each other. It's creating this kind of linear composite and comparing the models to that. But anyway, let's go ahead and run a Manova, and I'm just going to call this fit1. And there's actually a command in R for Manova called Manova. So guys, we take our y, which we've created from y1 and y2, and we run a fit1. Just as we've done before, we would run summary fit1, and we get this output. Now, there's three major test statistics that people use. Actually, I guess there would be four, but there's three that you see the most. P-Li's trace, which is the one I'm using here, and you can see that our result is statistically significant. Another very common test is Wilks. Now you can see that Wilks has a little different value. It's running a little different distribution. Notice the degrees of freedom are different, and notice our p-value is a little bit different. Another commonly reported test statistic for I don't know if I can spell this correctly or not. It's hoteling lolly. Let's see if that works. Wow, cool. Okay, again, another commonly reported test statistic for Manova is this hoteling lolly, and again, it's different test statistic, but we also have different degrees of freedom in creating a little bit different p-value. Now, when things get really interesting, I've actually seen this before, is where you have maybe pill-ice trace that's statistically significant, and maybe Wilkes is not, or vice versa. That creates kind of an interesting paradox in running a Manova. Okay. So anyway, we've got statistical significance. So the group means across Y1 and Y2 appear to differ across group. Now we can get a little bit better indication of what's going on here by doing what's called a let's see, how do we do that? Summary dot ANOVA for fit 1. That's not what it is. It's summary.AOV fit 1. Yeah, okay. Now what this does is it breaks our design into across the different responses. So this allows us to come in and, you know, if you look at this table, this is just a classic ANOVA table. And it allows us to examine the differences across Y1 and Y2. So we're kind of creating a no-no here by breaking these things apart. But you can see, and I'm pretty sure I'm right on this, let me just, if we had run just a separate ANOVA of, say, Y1 across group, okay, well, we actually get the same thing. Okay, so that's exactly what, I guess, what this is doing up here. I thought it was actually a little bit, something else was going on, but no, I was wrong. So that's really what the summary.AOV does in Manova, is it just breaks it down and conducts two ANOVAs. So it gives us an indication. There's a statistically significant difference in Y1, and there's a statistically significant difference in Y2 across the groups K1, K2, and K3. Now, what I would probably want to do here is I would want to do some multiple comparisons. And the multiple comparison could work like this. Let's say that we want to compare you know, across K1 and K2, and then maybe K2 and K3. And again, let me go back up and, you know, make sure that you're understanding what I mean by K1, K2, K3. These are just the subsets of the group. If we do that, we could do something like this. So now we're going to conduct multiple comparisons. And because we're doing multiple comparisons, we'd probably want to control for the type 1 error rate by maybe lowering our threshold. Instead of 0.05, we may want to look at 0.01. So I'm going to run a fit 2 and a Manova, and I want to run my Y across my well, let's do something a little different here, across my group. And then I want to set subset equal. Now here's where the fun starts. We're going to use a trick that I found. Alright, this should work. Now, what that's going to allow us to do is it's going to allow us to break our Manova down and just do a comparison between group 1 and group 2. So if I do summary fit 2, you can see that I'm just going to compare groups 1 and K, K1 and K2, and you can see that it has statistical significance at the 0.05 level. However, considering that we're going to construct multiple of these, I'm not impressed. I would want this to be statistically significant at the 0.01 level. So let's go ahead and see. So I want to run this one instead of a fit 2. I'm going to call this fit 3. And instead of K1 and K2, I'm going to run this as K1 and K3. Now, I have statistical significance at the 0.01 level here, so this has my attention. And I'm going to run, as you would expect, one more. So I'm going to call this fit 4. And I want to compare K2 and K3. Alright. And I'm not expecting anything here, but let's see what happens. Okay, so again, at the 0.01 threshold, we would not have statistical significance. So again, let's control for the type 1 error rate, decrease our alpha value, and so guys, it appears that the difference in group means appears to be between the comparison of K1 and K3. Alright, well guys, I'm going to keep this one short. What I'll do is, I just wanted this video to be honest with you, I don't have much time this morning. I've got to get in and teach an undergrad class and then teach another grad class this afternoon. But I wanted to get just an intro to Manova up first, just to get you thinking about Manova. The next video that you get will be a very thorough example. We'll set up hypothesis. We'll go in and see how we report these values, do a little stronger interpretation, and we'll go from there, man. So guys, have a good one.